We've looked at things that look like that. We've looked at things that look like that, like this. Oh, sorry. Like these. Both of these are examples of what? What are these both examples of? One of them's a line. They're graphs of what? Of functions. They're both functions. Can someone tell me why these are both functions? They both pass a certain test. They pass the what? The what test? The vertical line test. Every vertical line, so no vertical line passes through more than 1 point. So any vertical line you draw passes through at most how many points? 1. Now, can you draw squiggly lines on a board where that vertical line test is not met? Yeah, so for example, you could have something that looks like this, right? This would be a relation, but not a what? A relation, but not a function. A relation, but not a function. Relation. Because all you need is one vertical line to pass through more than 1 point, and what does it automatically not become? It is not a function. So for example, this line right here, that's a vertical line that passes through how many points? 1, 2, 3. So is this a function? No. So the big set we're dealing with is the set of, we have relations right here. And on one side of this, these right here are going to be the functions. So all functions are relations, but what are all relations functions? No. So the way you can say this, a better way to do this diagram actually, a better way to do this diagram would be to say this. Let me do it a little better than this. Inside here, here are all of the what? Functions. Exactly. So what we're going to look at today are two different types of functions. Two different types of functions. So we're just looking at functions. But how do you tell if a relation is a function if you have a graph? What do you look at? You draw lots of what? Vertical lines, vertical lines, vertical lines, vertical lines. And if that any vertical line passes through the function more than once, it's not a function. It's just a relation. Okay, so they are inverses of each other. Now, another way to look at them are these blob diagrams, and it's easy to see something that's really, really important. We are looking at, I told you, we're looking at two types of functions. We're looking at two types of functions. Those types of functions are going to be one-to-one functions and functions that are not one-to-one. In a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to one x value. So for example, on this one right here, is this a function right here? Is the one on the left a function? Yes, it is. It is a function. It is a function. For example, what is 2 squared? What is negative 2 squared? Can you plug in different values into a function and get out the same thing? Yes. You can plug in different values into a function and get the same thing. So again, is that a function right there? Sure. Could you find a function where you plug in 2 and get out 7 or plug in 3 and get out 7? Yes, you can. But is this a one-to-one function?
No.
No, because two numbers, two x values go to one y value. One-to-one functions, you can only have one arrow going between any two numbers. Yes?
So that's a relation?
That would, no. Both of these are functions. Both of these are functions. Both of them are functions. Remember, the blob goes like this. You have relations, right? And then inside relations, you have functions. But then functions get divided into one-to-one and what? Not one-to-one. So yes, it is. Everything we look at technically is a relation, Noir. It is true. Like the big set, it's basically like saying like, we are all people, right? And like, we are in this Algebra 2 class. And some of us are on this side of the room and some of us are on that side of the room, right? So the biggest set is we are all people, right? But the idea is we're looking at the smallest one. So I'm trying, if I asked you, if I gave you this right here, you would say, well, this is a function and it's not a one-to-one function. What about this one right here? Is that a function? Yep. Is it a one-to-one function? Yeah. There's no repetition. No same x value goes to two different y values, and no same y value goes from two different x values. Yes?
They look the same on a graph.
What?
They look the same on a graph.
No, they look different. We're going to see what these look like in a second. So first we're looking at what it looks like numerically. Essentially what it looks like algebraically. The inverse of f of x. What does it not mean? 1 over. It does not mean 1 over the function. Sometimes the inverse will be 1 over the function, but will it always be 1 over the function? No. So when you see f to the negative 1, do not do 1 over f of x. Okay? I understand this is a little different. I usually don't show you things like this because what are you going to always remember? That, but what you should remember is not that. Okay? So, this is really important. An inverse is a one-to-one function written f to the negative 1 is the set of all ordered pairs of the form yx where xy belongs to f. What that means is if you have a function, Liv, and your function has the point 2, 3 on it, what point has to be on the inverse? 3, 2. If you have a point 7, 9, what has to be on the inverse?
9, 7.
9, 7. You literally just flip the x and y values.
So f of negative 1 is 9, 7.
If that would, it would be, no, that would be the inverse of that point. Yes.
Yeah.
So if you took 7, it would map to 9, but if you did the inverse, 9 would map to 7. You just flip them. So if I gave you a set of points and said this is a function, how would you graph the inverse?
Just
Flip all the x and y values and graph those new points. That's all you would do. But you asked a good question, Nick, which is, what does this look like? That's really, really, really important. Before we do that, I want you to take a look at 3 examples. These are all functions. I want to know, are they one-to-one or not? So take a look at these 3, and there's 3 functions here. There's a, b, and this is all, by the way, this is all one function right here. That's not 2 functions. That's just a chart spread across 4 columns. Do it silently and tell me, do you think which ones are functions, which ones aren't functions? Try that right now. No, it's not. There's a couple reasons, right? 1 goes, so 2 has 1 map to it, but also 2 has 2 map to it. Also, there's another problem right here as well, right? So this is not 1, 2, 1.
But it's a function.
It is a function, sure. It is a function. Can you repeat y values? Yes. Can you repeat x values, though?
No.
No, you can't repeat x values or it's not a function. It wouldn't pass the vertical line test. What about b? What do you think?
It's a one-to-one.
It's 1-to-1. Yep. What about this chart right here? Is this 1-to-1?
Yeah.
No. Look, it even highlights it. I was trying to figure out how to paste in black and white. I'd really like that ability to take a picture, like clip a picture and then go to black and white. Look what happens. 2000 goes to 13, but also 2006 goes to 13. So is this 1-to-1? No, it's really important. I haven't really told you why. Like, you don't understand, like, what's the point of this? We'll get to that in about 2 minutes. In that one?
No.
So where do you put y?
Well, y equals.
Exactly. This is y equals 2x plus 1, right? So what does this first step say right here, step 1? Interchange it. So all x's become y's and all y's become x's. So what does this become?
X equals 2y plus
2y
1.
plus 1. And then step 2, solve for y. Have we solved for y before? Yeah. What do we subtract first?
Negative 1.
No, we subtract 1.
Okay.
Equals 2y. So what does y equal? X minus 1 over 2. And then what's the third step say? It says replace y with that f inverse. So f inverse of x is equal to, and one way you can write this is 1/2 x minus what? Half. Minus 1/2. So here's the deal. We just found the actual function. Is that a line? Yeah, the inverse of a line is going to be a line. Now, let's just see if we believe it by testing 1 point. Let's just test 1 point. So what happens if I let x equal 1 right here? What's f of 1? 2 times 1 plus 1 is what? 3. Let's try f inverse of 3. That's going to be 1/2 of minus. So it's going to be 3/2 minus, which is 2 over 2, which is what? Is that what we should get? Yes. Now, testing 1 point. Does testing 1 point prove that this is an inverse? No, but is it a good sign?
Yeah.
If we plugged in 1 and got out 3, but we plugged in 3 and got out 7, what would that tell us? Definitely not the inverse. How many points do you need to show it's not the inverse? Just 1. Just 1. But assuming we've done all the work right, it is the inverse. So it's good to test 1 point just to be a little bit more sure of yourself, right, if you have time. But again, just because 1 point works doesn't mean all of them work. No. But the point is, how many are all the points? Exactly. So we don't have, other than making sure your work is correct, Mark, right now, we don't have another test to see if it works. Or there's other ways to kind of believe it more, and one way is this, because here's the deal. If you do the math wrong, it usually messes up all the points. It's really hard to like pick the right, wrong, like a false positive. Like if this was the wrong inverse, it'd be really hard to find a point that actually works. Do you understand what I mean? Like it is possible for a couple points to work, but mostly lots of them are not going to work. Okay, so let's have you do one. Let's say I said f of x is equal to, how about this? Let's say 3 over 2x plus, let's say 4. Find me the inverse of that function. What do you do first, Nick? What's the first thing I should do? Yeah, I mean, so I say I have y equals this, right? So you interchanged. So you did what? X equals 3 over 2 y plus 4. So x minus 4 is equal to. So yeah, most of you, I saw some of you do this. You wrote, and this is correct, it's not done, y is equal to x minus 4 over. But that's equal to x minus 4 times what? Over 3. So that's equal to 2/3 x minus 8/3. So the inverse function, the clean version that I would like, f inverse of x is equal to 2/3 x minus 8/3. Now, could you test one point?
Yeah.
Yeah, you could. Did you anybody test a point? Did it work, Hannah? Yeah, it did work. Yes, a non-one-to-one function and see what happens. So, for example, what does this look like? Y equal x squared plus 2. What shape is that? We literally have spent 3 weeks looking at these. What shape is that? Parabola. It is not a line. It is a parabola. That is correct. It is a parabola. What is the y-intercept? 2. So let's say that's 2. It looks kind of like this, right? So if we were to plot some points, this point is 0, 2. Let's say that one's going to be, if I plug in 1, what do I get if I plug in 1 into that? 1, 3. And if I plug in negative 1, what do I get? Negative 1, 3. Right? Are we okay with those points? Yeah. So could we write those points in a table if we wanted to? Sure. So what was it? It was negative 1, 0, and 1. And what were those points? 3, 2, and 3. So what did I say you have to do if you wanted to get the inverse? What do you do if you want to get the inverse? Yeah, you switch them, you swap them. So the inverse, you just switch them. You keep the same labels, but you switch them. So if we switch these, what do you end up with? 3, negative 1, 2, 0, and what? 3, 1. So I'm going to use green here. Well, actually, I'll use blue so you can see it here. So this is going to be the inverse. Where is 2, 0? 2, 0 is right there. There's 3, 1, and there's what? That's 3, negative 1. What point is this? 3, positive 1, and this one is 2, 0. If I were to connect these, what does it look like? Yeah, which way is it pointing? To the right. Is that a function? Oh, wait a minute. The original function we used, the red one, was that 1-to-1?
Yeah.
No.
No, it was not. It was not 1-to-1. Why wasn't it 1-to-1? Doesn't pass the horizontal line test. If you take the inverse of a non-1-to-1 function, what do you end up with? A non-1-to-1 function. A non-function.
Yeah.
So look, the reason we want 1-to-1 is because when we invert 1-to-1 functions, what do we end up with? Functions. If you invert a non-1-to-1 function, what do you end up with? Something that isn't a function. Is the blue a function? No, the blue is not a function. Why not? It doesn't pass the vertical line test. What happens to a horizontal line when you flip it? What does it become? Ah, okay. Is this kind of making sense now? Is the red one a function? Yes, it is a function. Is the red one a 1-to-1 function? No. When you invert something that is not 1-to-1, it creates something that is not a function. We like dealing with functions, so if we're going to invert something, what do we like it to be? 1-to-1. They are inverses of one another, but is the blue one a function? No. The blue one is not a function. There are many vertical lines that don't work, right? Another way to see this is to do it algebraically. Y equals x squared plus 2. If I wanted to find the inverse, what do? You interchange it, right? So x is equal to y squared plus 2. So x minus 2 is equal to y squared. What do you have to do to both sides now? So y is equal to what? That's half of it. Plus or minus, right? So what the upper half of this thing, you see this part right here, what is that? Y equals the positive x minus 2. And what's the bottom one? The negative one. Whenever you see plus or minus, that's really going to mean not a function. So we like 1-to-1 functions because when we take the inverse, they stay functions. If you start with something that isn't 1-to-1, what does it become? Not a function. We like functions. We want to stay with functions. That's why we like 1-to-1-ness.
That's parabolas.
So basically, all parabolas are not 1-to-1. So are we ever going to really invert parabolas? No. Not really. I might ask you, is this going to be a function when you're going, no, it's not.
So we're going to invert lines.
Line. Here's the second set of functions. There's the function and its inverse. Do you notice anything similar about the relationship? So again, let me do this for you here. Let me take this here. So let me show you the pairs here. Where are the pairs? The pairs are, here you go. Well, they're going to be, yeah, that's true, but let's see if you can figure it out here. So there's this. There's one pair, which is this function right here, and this function. There's one pair. You see that one? And then there's this function right here, and this function. Can anybody tell me what the relationship is? They do intersect. They both intersect, right? They intersect at different places, but can you tell me how you transform one into the other? You can apply the same rule to both sets, and you'll get the other function. Anybody see it? I'll give you a hint. It involves folding.
Yeah.
It involves folding. There's some symmetry. What's the symmetry? There's a symmetry across something. Anybody know what it's symmetric across?
The axis of symmetry?
Yeah. What is the axis of symmetry on this one? I'll give you. Can you if you had to fold the purple onto the purple, where would the dotted line be? Where would the fold be?
On the intersection, right?
It would be, yeah. You have to. You know it would be here, right? And you know it would be here. So what do you do with those 2 points? Connect them. See this right here? What is this? That is the line of symmetry. Anybody know what that function is? I give you a hint. It's really simple.
It's like x over y. Oh, you're right.
It's y equals what?
Yeah,
It's just y equals x. All inverses are reflections across the line y equals x. So what do I mean by that? You get this picture right here. This picture right here. So if you have the point AB and you flip it to make it BA, what you've done mathematically is make it the reflection across that line. We're not going to do the proof of that, but you just need to believe it. Are you okay with just believing it? So what does that mean? What's the angle? What's the angle right here, Mar? 90 degrees. And this distance has to be the same as this distance. So one thing you can do is if you know that this point is here, where's the other reflection going to be? Or the reflection. It's going to be right about here. And let's say I have this point right here. Where's
Be on the other side of the dot.
So look, this right here is a 90 degrees and has to be that distance. This has to be the same distance and 90 degrees. So if you had a path, kids, if you had a path that looked like this, what would the inverse look like?
Yeah.
Like that. If you fold on the blue line, what do you get? The same thing. If you fold, that's how you get it geometrically. So theoretically, one thing I remember doing long ago when I was in high school learning about this, we would draw functions with pencil and like put a lot of pencil lead on the paper, something like graphite, right? We would then fold the paper along the lines y equal x, and we tap it down, and then what would you get? You would print it out on the other side. You know what I mean? So if you fold across, so this right here is a good way to get a general idea. Can it be really tricky drawing it? It can. It can be really tricky, but it's also a good way to know if something isn't an inverse. What I mean by that is, let's go up here. Do you see the 2 green right there? Let's say instead of this, let's say you had this green. Can you see me highlighting right this one right here? So let's say instead of the second green, you had something like this. Is that in any way the inverse? No. So it's really easy to pick out pairs when the pairs are present. They will look symmetric. They'll look like something that's spun around that y equals x. Yes, Connor?